This next chapter talks about ancient civilizations and how astronomy impacted their lives, and it takes you through kind of a history of from ancient understandings of astronomy, solar system objects, motion of the stars, and so on, to more modern understanding, thousands of years ago still even, to even more modern understandings of today, maybe roughly 400, 500 years ago. And then eventually we'll talk about even more modern understandings, within the last 50, 100 years or so. But if we go way, way back, thousands of years ago, people were, looking at the sky, looking at stars, looking at the moon, the sun, and really making observations of how those objects moved. And if you imagine back then, they had no lights, maybe some campfires, but the skies were extremely dark, and you could see a lot more on a typical night than you can today. Still, maybe only about 2,000 stars in reality because of the sensitivity of the human eye, but still, no matter where you went on the earth, the skies were very dark. So that's what they did. They spent time watching the sky and watching the sun and the moon and the planets and so on. And they really understood the motions. They didn't know why they occurred, but they saw these patterns. So they used these patterns to develop timekeeping ways, not necessarily mechanical clocks, but ways of keeping time by tracking the objects in the sky, tracking the seasons, knowing when to plant their crops, when to harvest, when it would be starting to get cold or warm, and so on. Developing a calendar after seeing the patterns, they could see a repetition over a longer period of time. They developed a yearly calendar. The lunar cycles established the different months of the year, monitoring the planets and the stars, established certain understandings of what's going on in the sky, predicting eclipses, predicting lunar and both solar eclipses over time. They could determine when the next one would be, as well as a bunch of other things. There was an area in Africa, Central Africa, about 8,000, a little over 8,000 years ago. There's evidence that there were people there that planted their crops based on what the moon looked like, based on a crescent moon. So if you look at the crescent moon, if it looks like this and it's sort of kind of pointing in a particular direction, not straight down, but kind of off to the side a little bit, almost straight down, that implied a certain time of the year. And that indicated that the weather is going to be fairly dry. As the moon tilted a little bit more and a little bit more, they would know that they were getting into the wetter season, so maybe it's time to start planting their crops. And then that tilt changes throughout the year, and it tilts kind of flat again, and then it tilts off to the right a little bit, and by the time as it starts to tilt off to the right, they realize that that there's this sort of pattern that matches the weather, and they said, okay, we're starting to reach the end of the wet season, so another dry season is coming, and so now would be the time to maybe start harvesting the crops or doing maybe some other planting of some sort. And yeah, they believed that there was probably a connection between the moon and the weather. We know that that's not the case anymore, but just because of the way the climate patterns were in that region and the patterns of the moon having these patterns, the lunar cycle is about a month long, the patterns were very much similar in terms of weather and the lunar patterns. So they had a pretty good way of determining what the weather was going to be like, on average, sort of, based on what the crescent moon looked like. Other places developed calendars. The days of the week were based on the 7 bright objects that move through the sky, the 5 planets and the sun and the moon. Sunday was named after the sun, Monday after the moon, and so on. We have big timekeeping devices. This obelisk, Egyptian obelisk, is a way of telling time. It casts its shadow in certain places, and depending on where the shadow is sitting, laying, whatever you want to call it, that tells them a particular time, the length of the shadow as well as the direction that it's pointing. So they had timekeeping measurements using these little stones around the edges as well as the shadow of the big obelisk that could tell the time. Stonehenge in England, completed about 3,500 years ago. If you look carefully at the way the stones are lined up and you look at some of the toppled ones and try to reconstruct it, it's clear that there are certain features that are lined up with certain astronomical phenomena. If you look at this picture, there's a big stone called the heel stone, and on the summer solstice, the sun rises right above that heel stone. And so it's lined up nicely with the center of this circular region of stones and the heel stone. And the sunset would be over here, the sunrise over here, sunrise in the winter, sunset in the summer. So all these different things were lined up with different risings and settings of the sun, and possibly other astronomical objects as well. So that was really, really early civilizations. And as time went on, later civilizations started to develop models. The Greeks were particularly good at developing models of why things were happening. And they developed models for why the planets moved in the way they did. And their biggest model was what was called the geocentric model. When you look up at the sky, it doesn't appear like we are moving. It seems like everything's moving around the Earth. So they came up with this model of the solar system called the geocentric model that said the Earth was at the center of everything and it wasn't moving. And everything was moving around us. One person in particular did some measurements of the Earth and gave some very strong evidence that the Earth was actually round. A lot of people thought that the Earth was flat, or some other, maybe a disc shape or some shape, who knows. But he showed that the Earth was actually a ball, and he had a pretty good estimate for the radius of the ball of the Earth. What he did is on the solstice, the summer solstice, he had a friend, perhaps, standing in a city called Cyan, and the sun happened to be directly overhead on the solstice. And so there was no shadow cast by this person. So you could imagine that this ray of light, therefore, went straight down to the center of the Earth. If it could, of course, it can't, but assume that ray of light could penetrate the Earth. It would go right down to the center of the Earth, because you assume that if you're standing on a ball, standing straight up, you're standing kind of vertically away from the center of the Earth. And then he compared the lack of shadow there to the fact that at the same moment there was a shadow if you stood in Alexandria, which was about 5,000 stadia away. A stadia is a certain measure of distance. So there's a certain distance that was known between Cyan and Alexandria. And there was no shadow on that day here, but there was a shadow here. So if we think about the Earth as being a ball, the sunlight would just go directly this way, and we could measure the angle between the sunlight hitting the top of the person's head and where it hits the ground. That angle is about 7 degrees. We could measure that angle of 7 degrees. Well, that implies that the angle, if you drew this line from the person down to the center of the Earth, that implies that this angle here is also 7 degrees, which means that distance from the Earth, or from Alexandria to Cyan, spanned an angle of 7 degrees. In other words, it took up 7 of the 360 degrees that go around the complete circle around the Earth. So 7 of the 360 degrees to go completely around the Earth. That distance was actually equivalent to this 500 stadia. So we can use that ratio, that comparison, to calculate the entire circumference of the Earth. And then we could use that to calculate the radius. And so the little calculation is done down here. And they come up with, in terms of stadia, they come up with a circumference of about 25,000 or 250,000 stadia. And if we convert that into kilometers, that's about 42,000 kilometers. A more modern value, more correct value, is about 40,000 kilometers for the circumference of the Earth. That's pretty close. This is a pretty good measurement. This is pretty accurate for 240 BC. And so that was good evidence that the Earth was actually a sphere, a ball of some sort, rather than something flat. And so the Greeks also, not only were they looking at models of nature and stuff, they were looking at motion of the planets and so on. And again, they talked about how everything seemed to be moving around the Earth. And so they thought that the heavens, when you look at things in the heavens, the moon and the sun, they look like perfect balls. They thought of everything in the heavens as being perfect. And so the Earth, of course, isn't perfect, so it's at the center, and below the surface is maybe hell, if you want to think about it that way. And above the surface, up into the sky, are the heavens, the perfect areas. So everything in the heavens is supposed to be perfect spheres, perfect circles, and so on. So they started thinking about the motion of the planets around the Earth, and they figured, well, the motion must be circular. And so the Earth must be in the center, and the sun and the moon and the planets and everything must be going around the Earth in perfect circular orbits. Well, if we back up a little bit, what that makes difficult to explain is something we talked about in Chapter 2, which is retrograde motion of the planet Mars. And we demonstrated how easily we can explain that by thinking of the Earth not being stationary but going around the sun. And Mars goes around the sun as well. So as the Earth is going around the sun, we see Mars near certain stars, near certain constellations. And as the Earth goes around and Mars goes around, Mars appears to move eastward across the sky. But as Earth overtakes Mars in its orbit, Mars actually starts to appear to go backwards. So from this point number 3 to 4 and 5, it looks like Mars is now going westward from 3, 4 to 5. And then Mars goes again back to the east. So this retrograde motion, this apparent backward motion, is something that we can easily explain by thinking of the sun at the center, not the Earth. But the Greeks around 200 or so BC, 150 BC, weren't really convinced that the Earth was moving. They were very convinced, in fact, that the Earth was stationary. So they held on to this idea that the Earth was stationary. It was a geocentric universe. And a fellow by the name of Ptolemy developed a model to explain this retrograde motion, what we call an apparent retrograde motion. He thought it was an actual backward movement of the planet Mars. So he developed this model of orbits based on circles of the planets around the Earth. And it was fairly complicated, but it was able to do a pretty good job at predicting the positions of planets for hundreds of years. And people used it. There wasn't much of a reason to think that it was wrong, because it did make good predictions. So that model looks something like this. The Earth is at the center, and it goes around on the planet goes around on a big circle, but on that big circle is called a deferent. On that big circle is a smaller circle called an epicycle. The planet actually goes around on that epicycle as the center of that epicycle moves on the deferent. And so the planet actually sweeps out a path like this reddish-brown path, orange, whatever color that is. And when the planet is kind of on the inside part of the epicycle, it appears to actually move backwards during that time. And then it's moving eastward, and then it comes around here, it's moving backwards again, and so on. So by placing these circles upon circles, and sometimes even more circles upon circles, Ptolemy was able to provide a pretty good explanation, at least in terms of what they thought was good, for this retrograde motion. What we think is we call it apparent retrograde motion, because we now know that it's not real. It just appears as if Mars is going backwards. This model actually suggested that Mars in fact was going backwards. So this was Ptolemy's model, and it lasted for a long time. There were people early on that thought this was wrong. For a long time there were people that thought this sun was at the center of the solar system. But it wasn't until about the time of Copernicus that we'll talk about, where he really provided some strong arguments against the Earth being at the center of the solar system. In summary, the ancients developed models, or the Greeks specifically developed more models of nature, and their models were able to make predictions. And the predictions agreed fairly well with observation, and so they didn't have a really good reason to say that their models were wrong. It wasn't until we were able to make much better observations, much more precise measurements, that we realized that their models were wrong. And then planetary motion in particular was explained with the Ptolemaic model of these epicycles upon deferents, and sometimes even epicycles upon epicycles. So in the next little video we'll talk about Copernicus and Kepler and Galileo and some other people who helped us really understand the motion of the stars, the motion of the planets in particular.